In this video, we are going to talk about orthogonal sets of vectors. This is our overview slide, which we will go over in 3 or 4 minutes, and then we'll go through each topic in more detail and more examples. We will start with the definition of an orthogonal set. So a set of vectors, u1, u2 up to up, is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, u sub I dot u sub j is equal to 0 whenever I does not equal to j. From there, once we have an orthogonal set of non-zero vectors in Rn, we have this theorem that says they are linearly independent and hence a basis for the subspace spanned by S. So an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. When we have an orthogonal basis, it's particularly nice because it's easy to find the coordinates of an orthogonal basis. So for example, if we have, according to this theorem, u1, u2 up to up is an orthogonal basis for a subspace W of Rn. So any vector y in W, we can find the coefficients in front of each vector by c sub j, that's the jth basis vector. C sub j is equal to y dot u sub j all over u sub j dot u sub j. So this is a nice, easy formula, as opposed to normally when we're looking for these coordinates for to write a vector as a linear combination of the bases, we would have a set of linear equations, and we would be row reducing the augmented matrix. Here we have a simple formula to do. Next, we will talk about orthogonal projections, which is useful when we want to decompose a vector y in Rn into the sum of two vectors. The two vectors include a given vector u and another vector which is orthogonal to u. So you can remember from physics, often you'd be given some vector y, and you would want to decompose it into an x component and a y component. This is much the same, but now you're decomposing it into a component of u and a vector orthogonal to u. Once we have this orthogonal projection, we can then apply a geometric interpretation to this theorem here when we were finding coordinates of an orthogonal basis. That is, this theorem then becomes a decomposition of the vector y into a sum of orthogonal projections. So we'll take a look at this. Next, we have an idea of orthonormal set. So that's a set that's not only orthogonal, but all the vectors are unit vectors. And because orthogonal sets are linearly independent and therefore a basis, these vectors then will form an orthonormal basis. We then follow up with a couple of theorems about matrices with orthonormal columns. So that's it for our overview. So we're ready now to start with our definition of an orthogonal set. If we have a set of vectors u1, u2 up to up, it is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. In other words, when you dot one of these vectors with another vector in the set, then it'll always be 0, as long as I does not equal to j. Our first example will be to show that the u1, u2, and u3 vectors below form an orthogonal set. I've taken each set of two vectors and I dotted them with each other. So I dotted u1 with u2, u1 with u3, and the only other pair is u2 with u3. Remember, we don't have to do u2 dot u1 because the dot product is commutative. So we have u1 dot u2, that's 3, 1, 1, dotted with negative 1, 2, 1, which gives us 0. u1 dot u3, which is 3, 1, 1, dotted with negative 1 half, negative 2, 7 halves. You can see that's also equal to 0. And then u2 dotted with u3 is our negative 1, 2, 1, dotted with 1 half to negative 2, 7 halves, which finally is equal to 0. So each pair is orthogonal, and therefore u1, u2, u3 is an orthogonal set. Since these vectors are in R3, I went ahead and drew them over here. So my first axis is for my first coordinate, my second coordinate axis, and my third coordinate axis, x, y, z, or x1, x2, x3. So for U1, that's 3, 1, 1. So I went 3 on my x1 axis, 1 on my x2 axis, so I'm somewhere around here. And then I go up 1 unit, and that gives me my U1. Next, I have my -1, 2, 1. So I go -1 over 2 units. So that puts me somewhere around here in the x1, x2 plane. And then I go up 1 unit. That's my U2. Finally, I have my -1/2, -2, 7/2. So I go approximately -1 on x1, -2 on my next axis, and then up 3 1/2. So this is my U3. So if I did a really good drawing, you'd be able to see that these three vectors are all orthogonal to each other. They're all perpendicular. They're at 90-degree angles. It's hard for me to see from my own drawing, and I really took a little bit of time to try to do it. But you'll just have to take my word for it. If I had done a good job and we were all really good at visualizing, we would see that these are all at 90-degree angles. Next, we have this theorem that if we have a set S of vectors u1, u2 up to up, that's an orthogonal set of non-zero vectors in Rn, then S is linearly independent and hence a basis for the subspace spanned by S. And before I go into a proof of this theorem, I do want to point out that in this case, our last example, u1, u2, u3, was an orthogonal set, and we saw that the graph u1, u2, u3 are perpendicular to each other, so we could use u1, u2, u3 as a basis for R3. So it would be a change of coordinates, a change of basis from our normal standard basis for R3, which is the I, J, and K direction. And now we are ready to start the proof. If we want to know if a set is linearly independent, we need to look at the homogeneous equation and ask ourselves, is there a non-trivial solution? Because that's exactly the definition of linearly independent. We take this homogeneous equation and we're going to dot both sides of the equation by u1. So we're going to have 0 dot u1 and then this right-hand side of the equation dot u1. Since we have this distributive property of dot products, then we can distribute in the u1, and I kind of went ahead and rearranged the terms. So we have c1 u1 dot u1, we have c2 u1 dot u2, plus up to cp u1 dot cp. So I did a couple of algebraic steps. I combined a couple of algebraic steps from here to here. But the next step is, since u1, u2 up to up is an orthogonal set, all of these terms over here are all going to 0 when I does not equal to j. These all go to 0, and we're left with c1 u1 dot u1. And also, since u1 dot u1 is greater than or equal to 0, that's a property of inner products, that must mean that c1 must be equal to 0. So this is our first conclusion. We can similarly conclude c2, c3, cp is equal to 0 using the same argument. Here, to get c1 is equal to 0, we dotted our homogeneous equation by u1. If we want to find c2 is equal to 0, we'll dot our homogeneous equation with c2, follow the same sort of logic, and we'll come to the conclusion that c2 is equal to 0. We can do the same for c3, c4, up to cp, and we'll find them all equal to 0, and therefore u1, u2 up to up is linearly independent. And not only is it linearly independent, it'll be a basis for the subspace spanned. On our overview sheet, we just proved this theorem here, that an orthogonal set of non-zero vectors is linearly independent and hence a basis for the subspace spanned by S. So then we can also define an orthogonal basis for a subspace W of Rn, and that's simply a basis for W that is also an orthogonal set. And next we have this theorem that tells us why orthogonal bases are nice. And that's because when you're looking for the coordinates of an orthogonal basis, it's done easily with this formula here. In particular, if we let u1, u2 up to up be an orthogonal basis for a subspace W of Rn, then for each vector y in W, the weights in the linear combination, when we write y as a linear combination of our basis vectors, the weights C1, C2 up to Cp, can be given to us by this formula. So C sub j, so in other words, like if we're looking for the C2 coordinate, C2 would be equal to y dot u sub j, or U2, divided by U2 dot U2. We are going to prove this theorem and then we'll do some examples. To find C1, we're going to dot y with U1. So y, remember, is a linear combination of our basis vectors. We're going to dot it with U1. And much like our other proof, once we dot it, we can distribute in, and I rearranged my terms. We get cu1 dot u1, c2 u2 dot u1 up to cp up dot u1. And again, we're going to use the fact that u1, u2, up is an orthogonal set, and all these terms where the u sub I and u sub j, where u does not equal to j, these all go to 0. So what we get, or what we have so far, is y dot u1 is equal to c1 u1 dot u1. And then just by using algebra, we can solve for c1. It will be y dot u1 over u1 dot u1. And similarly, for any c sub I, that's going to be y dot u sub I divided by u sub I dot ui. I have moved the theorem up here to make space for an example. We're going to use the set S, the three vectors we had in our last example that we've already shown was an orthogonal basis. So U1 is 3, 1, 1, U2 is negative 1, 2, 1, and U3 is negative 1 half, negative 2, 7 halves. Then we're going to express this y, 6, 1, negative 8, as a linear combination of vectors in S. So this is our goal. Y, which is equal to 6, 1, minus 8, is going to be C1, 3, 1, 1, plus C2, negative 1, 2, 1, plus C3, negative 1 half, negative 2, 7 halves. And we are going to find the C1, C2, and C3. We have done problems like this in the past, but now we're going to show how much easier it is when we know we have an orthogonal basis. It would be a very easy thing to plug into our formula here to find C1, but I really try to avoid memorizing formulas. But what I remember is because it's orthogonal, it has something to do with dotting it by each vector one at a time. So to get C1, I remember that I'm going to dot it with Y1, and then from there I just see what happens, and it works out. So you don't have to memorize this formula. What I do is I do Y dot U1. So that's going to be my 6, 1, negative 8 dot 3, 1, 1. And that's going to equal to this right-hand side dotted with U1. So that's going to be C1, 3, 1, 1 dotted with 3, 1, 1. Our C2 are 1, negative 2, 1 times our 3, 1, 1, plus our C3, minus 1 half, minus 2, 7 halves times 3, 1, 1. Then what I can see is that here I'm going to have on the left-hand side, I'm going to get 18 plus 1 minus 8 plus C1, I have 9 plus 1 plus 1, and then I'll see that C2, well, if I had remembered that because this is an orthogonal basis, I really don't even have to do these calculations, but I did anyway, just to show you. I have my negative 3, 2, and 1, so this goes to 0. And then I have my C3 over here, and when I do the multiplication, that will go to 0, 2. So what I am going to get then is on my left-hand side, I have 11 equals 11C1, which implies C1 is equal to 1. So again, if you're like me and you don't like memorizing formulas, you do have to remember you're going to write your y looking to be a linear combination of your basis vectors, and then you're going to dot the entire equation by one basis vector at a time. To find C2, we're going to dot with U2. So here I have my y times my U2 plus C1 times my U1 vector times my U2, C2 my U2 vector times U2 plus C3 U3 vector times U2. What that gives me is over here on the left-hand side, I'm going to get minus 6 to minus 8, and on the right-hand side, Again, I should just know, but I went ahead and did it anyway. This goes to 0, this over here goes to 0, and then we're left with C2 times 6, which gives us C2 is equal to minus 2. Finally, to get C3, I dot this equation of y written as a linear combination of the three bases vector with my final bases vector, u3. So here you can see I dotted the left-hand side, my y, with u3, and then my right-hand side, everything is dotted by u3, and that will give me C3 is equal to negative 2. These are the calculations I just did. I kind of shrank them down a little bit to give me some room. But what you can then do is verify that your y vector 6, 1, negative 8 is equal to C1 is 1 times U1, which is 3, 1, 1, plus C2, which is negative 2, times U2, which is negative 1, 2, 1, plus C3, which is negative 2, times U3, minus 1 half, minus 2, 7 halves. So you can verify this. I had mentioned at the start of this problem that we did know how to solve this problem. It would essentially be looking at this equation here with x1, x2, and x3. I mean, we've already solved for them, but instead of the 1, we would have x1 here, x2 here, x3. We'd have a system of linear equations, so we would be solving this augmented matrix, the column vectors with our solution vector, and that seems much more difficult than just doing these dot products. On our overview slide, we just finished this theorem here for finding coordinates of an orthogonal basis. So now we're ready to look at orthogonal projections. And again, that's towards the problem of decomposing a vector y in Rn into the sum of two vectors, two orthogonal vectors, one of them being a multiple of a given vector u. And the problem in particular is given a non-zero vector u in Rn. So here in blue I have my vector u. Consider the problem of decomposing a vector y in Rn, here's my vector y, into the sum of two vectors. One, a multiple of u, so some component of u, you're going to multiply u by some scalar, and then another vector orthogonal to u, so y is going to be decomposed into these two vectors, much like in physics. This is like in physics when you used to have, I don't know, maybe a ball was hit out this way, maybe it had some velocity equal to r, and then it was hit at an angle theta, and then you would decompose this vector into an x, a component along the x-axis and a component along the y-axis, right? You would use trigs, so the component along the y-axis would be r sine theta, the component along the x-axis would be r cosine theta, and in that way you could figure out how far it went along the x-axis, and you can figure how high it went along the y-axis, and those were considered two kind of orthogonal, two separate problems once you had your vector decomposed. And that's exactly what we are doing here, except instead of decomposing y into an x-coordinate and a y-coordinate of the standard bases, we're going to use a u-coordinate and then another vector that's perpendicular to u, which we will call a z-coordinate. So here we have our vector y is going to be decomposed into y hat. Y hat is just a multiple of u, which we have expressed here, y hat is a multiple of u, and z, where z is perpendicular to u. And also from that equation, y equals y hat plus z, we know that z is equal to y minus y hat, which we have expressed here and also in our graph. Starting with our equation, again, we want to express y as a sum of a multiple of u, so that's y hat, which is equal to alpha u, plus z, where z is perpendicular to u. And from this equation, we can solve for z. Z is equal to y minus y hat, which is equal to y minus, and y hat is just a multiple of u, so alpha u, where alpha is a real number. Taking into account our last condition now, z is perpendicular to u, well, z, which is equal to y minus y hat, is perpendicular to u if and only if z dot u is equal to 0. Substituting z is equal to y minus alpha u over here, and then dotting u, we get then y dot u minus alpha u dot u, which then implies alpha is equal to y dot u over u dot u, and our y hat is equal to y dot u divided by u dot u times our vector u. And again, this shouldn't surprise us because we're using the idea of orthogonal vectors, which is why this formula looks really familiar. But anyway, y hat here is the orthogonal projection of y onto u, and z is the component of y orthogonal to u. So often if we look at this in the picture, often we think of this projection as being if we took y and took the shadow of it onto our vector u, that's what y hat would be. Or we can think of this as projecting y down onto a single dimension. What would it be if it were on this single dimension? The last thing, I'm just going to repeat, this formula should look a lot the same as the coordinates of vector y using u as a basis because it is exactly the same. And the reason is we're using the same ideas of orthogonal vectors. I moved our ideas of orthogonal projections up here so that we could do this example. We're going to let y equal 7, 6 and u equal to the vector 4, 2. We want to find the orthogonal projection of y onto u and then write y as the sum of two orthogonal vectors, one in the span of u, using u, and the other orthogonal to u. I'm going to use this formula for now, but I am going to tell you you don't have to memorize it because it's the same exact formula as we had for the coordinates of a orthogonal basis. And I'm going to talk about that a little more in a minute. But for now, I'm just going to use the formula. So alpha is equal to y dot u over u dot u. So y dot u is 7, 6 times 4, 2, which is 40. And u dot u is equal to 4, 2 times 4, 2, which is 20. Which now means my y hat is equal to alpha, which is 40 over 20, times u, which is 4, 2, which is 8, 4. Now I'm going to look for my z, which is simply y minus y hat. So I have my y, which is 7, 6, minus y hat, which is negative 1, 2. So that means y is equal to 8, 4, which is equal to 2 times my u vector, plus minus 1, 2. So again, this is my vector in the direction of u. This is my vector that's perpendicular to u. One thing I do like to check, just to give me some warm fuzzies about my calculations, is I like to verify that the y hat I calculated and the z are orthogonal. So I dot y with z and I see it's equal to 0. So it doesn't mean that all my calculations are correct, but it looks like at least it passes one little check. Now next I'm going to graph this because I'm going to tell you, I want you to see the connection between this formula here that we have for projections and what we did previously when we found coordinates using an orthogonal basis. So here we have our vector y here, which is equal to 7, 6. So I graphed it here. This is my vector y. And I wanted y to be broken up as a vector u, some linear combination of u, and another vector that's perpendicular to u. That vector perpendicular to u is z. So in other words, I want to use u and z as a basis. And we know it's a basis because we designed z to be orthogonal to u, and orthogonal vectors are linearly independent, and there are two vectors, and we're in R2. So this is a basis. So essentially what we're doing is once we have y, we're finding it as, we're breaking it down into coordinates of u, z. So we're finding out what scalar multiple of u do we need, and it ends up we need to go out to 2u. That's y hat. And then we calculate what z is using our formula. And so what we have is that y is now a linear combination of z times 2u. So in other words, if we did our parallelogram, when we add z with 2u, completing our parallelogram law. Actually, I didn't draw this well. Okay, we would get the vector y written another way. We have our vector u, we have our vector z, we write y as a linear combination of u and z. And in this way, that's why this formula here, our alpha, looks exactly like the formula we had when we were finding coordinates of the first basis vector. And that is exactly the point number 3 here, the geometric interpretation of this theorem here for finding coordinates of an orthogonal basis. So this theorem here decomposes vector y into a sum of the orthogonal projections onto the basis vectors. Let me go back to that last example here, which I have summarized up here, and just a couple of other points. So if C is any other non-zero scalar, and if U is replaced by CU in the direction of y hat, then the orthogonal projection of y onto CU is the same as the orthogonal projection of y onto U. This was in your book, so I thought maybe we should kind of explain that. So again, y is equal to 7/6, u is equal to 4/3. Let's say we replaced u with some constant times u. Let's say that that constant is 3. So let's say u now is equal to 12/6. But our original u, which is up here, is 4/2. Then the orthogonal projection of y onto CU is the same. So it says that our orthogonal projection onto 12/6 is going to be the same as the orthogonal projection of y onto u. And so let's look at that. So y dot u then is equal to 120, and u dot u, you can verify these calculations for 12/6, is equal to 180. So alpha is going to equal to 2/3. But now alpha then is going to multiply by our new u, and we get the same 8/4 that we got over here for our projection. So the idea is, we scale this here. We scale the vector u by an additional 3 units, but that just means that later that our alpha is going to scale us back, because think about it in terms of our graph here when we talked about y was a linear combination of some, in this case, our first case, 2u plus z. Now, if we scale u and make u longer, that means we won't need to use, if u now is 3 times as long, so if u goes out to here now, we don't need to use the entirety of u, we only need 2/3 of u now. We just scale u back down, so when we add it to z, we get y. I thought that was kind of a weird comment. It's certainly true, but I think maybe this comment is meant to lead into the next comment, which is that this projection then is determined by a subspace L. In other words, the projection is determined not just by u, but all the multiples of u. So it's the line. So it's the subspace spanned by the line L, spanned by the vector u, because it's just scalar multiples of u. So the line through u and 0. So sometimes y is denoted by, sometimes the y hat is denoted by projection of y along L, and is called the orthogonal projection of y onto L. So this is our drawing again. So L now is the line. It's the span of u, all scalar multiples of u. And now if we want to find the distance from y to L, so that's going to be the length of the perpendicular line from y to the orthogonal projection of y hat. And this is the length of z, essentially. Z is equal to y minus y hat. So in this example, z will be equal to the, where's z? I can't find my z. Here is the length of z, which is -1 squared plus 2 squared, which is square root of 5. And one more time, going back to the geometric interpretation of this theorem. Where is that theorem here? Finding coordinates of an orthogonal basis. So if I then write y as a linear combination and I plug in my c sub j that we derived, I'm going to get in R2, for example, that I'm going to have this first c1 times u1 plus this next c2 times u2, and we can consider this as the orthogonal projection of y onto the subspace spanned by u1. And this whole term here is the projection of y onto the subspace spanned by u2. So again, here's our y. So you can think of, we're decomposing this vector into our two basis vectors, and you can think of it as the projection, kind of the shadow, or if we dropped y down onto this axis, or if we dropped y down onto this one singular axis. That would be the two projections. At this point, that we can decompose a force in physics into component forces, that's sort of what we've been talking about when we decompose these vectors into a sum of two vectors. So now we're going to talk about orthonormal set. And orthonormal sets are orthogonal sets of unit vectors. So U1, U2, up to UP is an orthonormal set if it is an orthogonal set and it's a set of unit vectors. So if W is the subspace spanned by such a set, then U1, U2, up to UP is an orthonormal basis for W, since the set is automatically linearly independent. I've moved my definition here for orthonormal sets, and then I have this example which looks long, but it's really just a bunch of dot products. So show that V1, V2, V3 is an orthonormal basis of R3. So orthonormal means we need to show two things, that it's orthogonal and then that they are unit vectors. So V1 is equal to 3 over square root of 11, 1 over square root of 11, 1 over square root of 11. V2 is equal to minus 1 over square root of 6, 2 over square root of 6, 1 over square root of 6, and V3 is equal to negative 1 over square root of 66, minus 4 over square root of 66, and 7 over square root of 66. So to show they're orthogonal, I'm going to take two vectors at a time, dot them together, and see that they are equal to 0. So here I did V1 dot V2. I have my first vector multiplied by my second vector, and I see that it's 0. I do the same for V1, V3. I see that it's 0. V2 dot V3 is also 0. So they are orthogonal. To show that they are unit vectors, I'm going to compute the unit, the length of each vector, which, if you recall, the length of each vector is just the square root of the vector dotted with itself. So here I have V1 dot V1, which is equal to 1, V2 dot V2, which is equal to 1, and V1 dot V3, which is equal to 1. Certainly when I square root the ones, I'm going to get 1. So I have 3 unit vectors, right? Technically, this is just V1 dot V2. The length is actually, right, the length of V is actually the square root of V1. Or, not V1, but dot V. But here I only calculated the V dot V, but I had to square root it to get the magnitude. But they are unit vectors. So in other words, because it's orthogonal and also unit vectors, this is an orthogonal basis. Well, it's orthogonal, so it is linearly independent, and it's a unit vector, so it's an orthogonal basis. Last, we have matrices whose columns form an orthonormal set, in other words, orthogonal and unit length, are important in applications in computer algorithms for matrix computations, and their main properties are given in the following two theorems. First, an m by n matrix U has orthonormal columns if and only if U transpose times U is equal to I. So this first theorem gives you a way of identifying if the columns of U are orthonormal, instead of doing all those calculations we did in the last example. We can check this. The second theorem, let U be an m by n matrix with orthonormal columns, and let x and y be vectors in Rn. Then, first, the length of U times x is equal to the length of x. That's kind of nice. And ux dot uy is equal to x dot y. And then ux dot uy is equal to 0 if and only if x dot y is equal to 0. I moved our two theorems over here so we could do our first example for matrix U given here and vector x given here. Notice that U has orthonormal columns and U transpose U equals I. So you're sort of given this fact, U transpose U equals I. Verify the length of Ux is equal to the length of x. And we have that U is equal to the 3 by 2 matrix with column vectors 1 square root of 2, 1 square root of 2, 0, and 2 thirds, minus 2 thirds, 1 third, and x is the vector square root of 2, 3. And again, we're given that U transpose, which is just this column is our first row, and the second column is our second vector times U, and you can do the multiplication, but it's equal to the identity matrix. To verify, first we're going to do ux, so u times x. Here I have, what is this? This is going to be 1 times plus 2, so that gives us 3. And then here we have 1 minus 2, which is minus 1, and then we have 1. The length of ux then is equal to my 3 minus 1, 1, times 3 minus 1, 1, square rooted, which gives me the square root of 11. The length of x is our square root of 2, 3 times square root of 2, 3 square rooted, which also gives me square root of 11. So we have verified this. I have one more observation. An orthogonal matrix is a square invertible matrix U such that U inverse equals U transpose. I have copied my information about orthonormal sets, the two theorems about matrices with orthonormal columns, and my last observation, an orthogonal matrix is a square invertible matrix such that U inverse equals U transpose. And I'm looking at this vector U from our previous example in this example now. So U is equal to the 3 by 3 matrix with the first column vector equal to 3 over square root 11, 1 over square root of 11, 1 over square root 11. The second column vector equal to minus 1 over square root of 6, 2 over square root of 6, 1 over square root of 6, and the third column vector equal to negative 1 over square root of 66, negative 4 over square root of 66, and 7 over square root of 66. And in a previous example, we have shown that each of these column vectors, v1.v2 is equal to 0, the v1.v3 is equal to 0, the v2.v3 is equal to 0. So all these three vectors form an orthogonal set. And then we also verified that v1 dotted with itself, when you square root it, it gives you a norm of 1. Our second column vector will give us a norm of 1, and our last column vector gives us a norm of 1. In other words, these three are unit vectors, and therefore they form an orthonormal basis, and it's square. So an orthogonal matrix is a square invertible matrix U such that U inverse equals U transpose. So theoretically here, that means we can take U transpose, taking this column, making it our first row, taking the second column, making it our second row. The third column becomes our third row, and that will be equal to U inverse. So I'm going to show you that U transpose then here times U is equal to the identity matrix. So I'm going to claim that's part of my proof of U transpose is equal to U inverse. Technically, I should also do U times U transpose is still the identity matrix, since matrix multiplication is not commutative. But anyway, I'm only going to do this half because this is the one that's easy to see, and I don't actually want to do the arithmetic. So let's do the U transpose, which I have written here, and I copied it over here. So U transpose is the 3 by 3 with column vectors 3 square root of 11 minus 1 square root of 6 minus 1 over square root of 66. The second column is 1 over square root of 11, 2 times square root of 6, minus 4 times square root of 66, and the last column is 1 over square root of 11, 1 square root of 6, 7 over square root of 66, and then our U matrix here, which I'm not going to read out. But when I multiply, you see I'm multiplying this first row times the first column, and you'll recognize this first row is the first column of U, and then when I multiply by the first column of U, that's right, the first column of U. So this is U1.U1. Here I have U1.U2, and then I have U1.U3. Next, I take my second row, which is actually U2, and I have U2.U1, U2.U2, and U2.U3. And then this last row is U3, so I have U3.U1, U3.U2, and U3.U3. And again, because they're orthonormal, all these other things when I is not equal to j, when we're not on the diagonal, are all going to go to 0. And again, because we're orthonormal, when we take the length of each vector, it's going to equal to 1. So that kind of is part of the proof that now U transpose is equal to U inverse. And you can see why that happens, again, because they are orthonormal vectors. Now that we've gone over all the concepts for this video, I have 4 more problems for you, but I'm going to suggest after you hear each problem statement, you pause the videos and give the problems a try before you look at the solutions. These are the 4 additional problems. The first one is to let u equal to minus 1 divided by square root of 5, 2 divided by square root of 5, and u2 equals 2 divided by square root of 5, 1 divided by square root of 5. Show that u1, u2 is an orthonormal basis for R2. Problem 2 is to let y equal 7, 6 and L equal to the span of the vector 4, 2. We've seen this vector before, and actually this is from based off of a previous example. Compute the orthogonal projection y hat of y onto L using u equals 2, 1 instead of 4, 2. The third problem is let u, and we've seen this matrix before too, let u equal to the 3 by 2 matrix where the first column vector is equal to 1 over square root of 2, 1 over square root of 2, 0, and the second column vector is equal to 2 over 3, minus 2 over 3, and 1 over 3, and our first vector x is equal to square root of 2, 3, and our vector y is equal to minus 3 square root of 2, 6, we want to verify that u times x dotted with u times y is equal to x dotted with y. And again, you might look back because we've worked with this matrix before. The last problem is let u be an n by n matrix with orthonormal columns. Show that the determinant of u is equal to plus or minus 1. For the first problem, we have our vector u1 and u2, and we want to show it's an orthonormal basis. So first we do u1 dot u2, so here's u1 times u2, and we see that's equal to 0. And then we do, actually there's only 2 vectors to dot with each other. We could do u2 dot u1, but we already know that's going to be equal to u1 dot u2. So it's orthogonal. They're linearly independent, so it forms an orthogonal basis. If we want to show it's an orthonormal, we also need to show that they're of unit length. So u1 dot u1 is equal to 1, so when we take the square root, it's going to have length of 1. u2 dot u2 is equal to 1, so when we take the square root, it'll equal to 1, and that's its length. It's equal to 1. Therefore, we have an orthonormal basis. Our second problem, we have a y equals 7, 6, and L is equal to the span of 4, 2. Compute the orthogonal projection y hat of y onto L using u equals 2, 1 instead of 4, 2. So alpha then, we're going to have is equal to y dot u, and we're using 2, 1 instead, over u dot u. So y dot u is 7, 6 times 2, 1 is 20. U dot u is our 2, 1 times 2, 1, which is 5, which means our alpha now is 20 over 5, which is 4 times 2, 1, so it's equal to 8, 4. So this is the orthogonal projection. It's the same as orthogonal projection as 4, 2 for reasons we had discussed in the video. Problem 3, we wanted to verify that ux dot uy is equal to x dot y. So here I have the calculation of u times x, which is equal to 3, negative 1, 1, and u times y, which is equal to 1, negative 7, 2. So ux dot uy, then I have my 3, negative 1, 1, times my vector 1, negative 7, 2 is equal to 12, and my x dot y is equal to square root of 2, 3, times my negative 3 square root of 2, 6, and that's also equal to 12. So here we have verified that ux dot uy is equal to x dot y. And I'm going to add that this is a direct kind of consequence? No, a direct illustration of this theorem here, that because u has orthonormal columns, this was a previous example in our video, then this property here, property B, holds. Problem number 4 is let u be an n by n matrix with orthonormal columns. Show that the determinant of u is equal to plus or minus 1. So we're given u is an n by n matrix with orthonormal columns. So we have this theorem that an n by n matrix U has orthonormal columns if and only if U transpose U is equal to I. You can see that theorem right over here at the bottom of our overview page. So I just wrote that here. since it's orthonormal, we know U transpose U is equal to I. Taking the determinant of both sides of the equation, I get the determinant of U transpose U is equal to the determinant of I. Then we have this theorem from, I don't know, a long time ago when we talked about determinants, that if A and B are n by n matrices, then determinant of AB is equal to determinant of A times determinant of B. So here it is an n by n, it is square. So determinant of U transpose U is equal to determinant of U transpose times determinant of U. Then again, we have another theorem from a long time ago that says determinant of A is equal to determinant of A transpose. So here we take the determinant of U transpose, that's just equal to determinant of U then. So we have determinant of U squared is equal to, and the determinant of I is equal to 1, which means determinant of U must be equal to plus or minus 1. To review what we've gone over in this video, we talked about orthogonal sets. So a set of vectors u1, u2 up to up is said to be an orthogonal set if each pair of distinct vectors from the set are orthogonal to each other. In other words, I dot uj is equal to 0 whenever I does not equal to j. Then we have this theorem here that said if we had an orthogonal set of non-zero vectors in Rn, then the set of vectors are linearly independent, and hence they are a basis for the subspace spanned by S. And finally, once we have a basis that is an orthogonal set, then we call that an orthogonal basis. We saw the nice thing about orthogonal bases is if we want to express y as a linear combination of the bases, in other words, we want to find the coordinates c1, c2 up to cp, that we could dot y with each of the bases one at a time. So if we dotted it with u1, we could find that all these other terms go away, and then we can solve for c1 is just equal to y dot u1 over u1 dot u1, which was our formula here. And again, the thing I just said is exactly how you derive this formula, so you might avoid memorizing that formula if you'd like. And then we talked about orthogonal projections, was the problem of decomposing a vector y in Rn into the sum of two vectors, one of the vectors being a multiple of a given vector u, and the other a vector orthogonal to u. Much like in physics, when we decomposed a force into components in the x direction and y direction, here we're decomposing a vector y into a vector u and then a vector orthogonal to u. And we talked about how our projection, which will be then equal to some multiple of u, that multiple, that scaling factor alpha, is the same thing as what we did when we found coordinates for an orthogonal basis, and that was no accident. Again, the scaling factor of the projection is the same formula that we used for finding the coordinates of an orthogonal basis. Not by accident, for reasons that we covered in our video. And also that is essentially the geometric interpretation of this theorem up here for finding coordinates of an orthogonal basis, is that essentially what we're doing when we find these coordinates is we decompose the vector y into a sum of orthogonal projections. Last, we talked about orthonormal sets, which are simply orthogonal sets where each of the vectors is of unit length. And then, since it is orthogonal, it is linearly independent, so we also have a basis, and if it's unit length basis, then we call it an orthonormal basis. We talked about matrices whose columns form an orthonormal set are important in applications in computer algorithms for matrix computation. We had their main properties are given by the following two theorems, that we can identify if a matrix has orthonormal columns by calculating U transpose U, and if it's equal to I, then we have orthonormal columns. The second theorem, if U is an n by n matrix with orthonormal columns and x and y are in Rn, then the length of ux is equal to the length of x, ux dot uy is equal to x dot y, and ux dot uy equals 0 if and only if x dot y is equal to 0. And our last note is an orthogonal matrix is a square invertible matrix U such that U inverse equals U transpose. So that's it for this video. Thank you for watching.